The purpose of this lab is to compare the difference between the observed position of an object and its predicted position using the momentum principle through a computational model. I observed the motion of a rolling marker with the assumption that the friction was small enough to allow Newton's second law to apply. Position and velocity were found using these models. The system consists solely of the marker, and the surroundings are everything else, including the surface of the table and the push at the beginning. This is my clip of the marker being rolled. The clip starts when the marker begins rolling and the net force at this point is 0. The first frame has the origin of the system set at the center of mass of the marker at time 0, and the negative x-axis shows the marker rolls to the left. If the positive x-axis and the negative x-axis were switched, the value of the x position would be positive instead of negative. Had the marker been rolled on a surface that was not flat, the net force would not have been equal to 0 and the velocity of the marker would not have been constant. Therefore, our model would not have applied. The point masses were at the center of the marker as it rolled, and the measurements were calibrated to the diameter of the marker as 0.0778 meters. This is a model based on Newton's second law, which is also known as the momentum principle. This part of the model code shows the visualization and graph initialization of the data, as well as the system properties and initial conditions. The system mass is set to the mass of the marker, which is 0.008 kilograms. And the initial conditions for the marker position and the marker velocity are shown here as vectors. We got the initial conditions for the marker velocity and position from the experimental data. Here we set the initial time to 0 and delta t as 0.033 because this is the amount of time between each time step in the experiment. We also set our calculation loop to go while t is less than 4.2 because this is how long we go in our experiment. The momentum principle states that the object's velocity is equal to the previous velocity plus the net force divided by the mass of the marker multiplied by delta t. And the object's position is equal to the previous position plus the average velocity times delta t. We see this in the code here, where I've highlighted the marker position update formula and the marker velocity update formula, which I derived from the momentum principle, which is also known as Newton's second law. We can run this program to get this model and gives us this position versus time graph, which we can observe is a linear graph. This is due to a constant velocity. We see this in the next graph. The velocity versus time graph is a straight linear line at a constant velocity. We can then take this data and place it into a spreadsheet program which can graph our data for us. Here's a graph that shows the predicted versus observed position of my data. The model data is represented by the blue line, and the experimental data is represented by the red line. There is a disparity between the data because the net forces in the model are set to exactly 0. But in the experiment, there are other factors, such as the higher friction, that could make the graph not completely linear. However, my observations can still be predicted well by my computational model because the marker rolls at a constant velocity. We cannot state for certain how many forces are acting on the marker, but we can assume it experiences some kind of frictional force that is almost equal to the force of the roll. In conclusion, the computational model that I constructed for this experiment predicted the observed position data accurately. Although the frictional force, as well as other outside forces, might have impacted the velocity of the marker, and therefore the position, the computational model predicted the position of the marker well. And we would expect the shown disparity because the model predicted a further location than the experiment showed. Which makes sense because in the experiment, with a higher frictional force, the marker will roll slower and be at a smaller x position. This was Lab 1. Thank you for watching.